Good day and welcome back for part 2 of our discussion on integration by parts. Let's begin with a reminder. Integration by parts is our first more advanced technique of integration, and it undoes the product rule of differentiation. It has the following form. The integral of u dv is equal to uv minus the integral of v du. So note, integration by parts does not solve the integral for us. What it does is hopefully expresses it in terms of a simpler, easier to evaluate integral. When applying integration by parts, we need to make a choice for u and dv. And a general rule of thumb at this point, and we'll get a bit more specific as we go along, is that at a minimum, dv needs to be something you can integrate, and ideally, u will become simpler when you differentiate it. And as we continue on our discussion, we are also going to want to pay particular attention to what scenarios or what functions are best suited for integration by parts. And at this point, let me just note what we've seen so far. So integration by parts works well for functions of the form, what we've seen anyhow, x to the e to the x. And to foreshadow just a bit, I would say it works well for any polynomial times an exponential. So that could be an x squared, x cubed, x to some other power. And in general, this could also be something to think about for x times f of x. And we've also seen it work well for integrating an inverse function like arctangent. And there's nothing special about arctangent. It's really just the fact that it's an inverse function. It would work just as well if we were integrating arcsine, natural log, or other similar types of functions. What I would like to do now to continue on our practice is for the next example, anti-differentiating x cosine x, I would like you to pause the video and give yourself maybe 90 seconds to 2 minutes to evaluate this integral. Hopefully at this point you've paused the video, you've evaluated the integral. If not, I'll give you a hint. Use integration by parts. So applying that hint, when we use integration by parts, we of course need to make this choice. What's going to play the role of u? What's going to play the role of dv? Now ideally, u is going to be simpler when we differentiate it. dv is going to be something we can integrate. And if we can choose u to be x, and that's not always the case, but if we can, that's a rather convenient choice because it very clearly becomes a simpler function. And if dv is cosine, we certainly can integrate that. Its antiderivative is sine. So integration by parts tells us uv minus the integral of v du. That is, we're going to have x sine x minus the integral of sine x dx. So the x sine x comes down for the ride. Recall the antiderivative of sine of x is minus cosine x. Minus a minus makes it a plus, and we have a plus c. So this is a scenario where integration by parts works out quickly and efficiently. For the next example, natural log of x, it's no surprise that we are going to use integration by parts because that is our topic of interest. But note, this falls into the second category I mentioned previously. Integration by parts can be used to integrate inverse functions. Remember, when we anti-differentiated arctangent, we noted that there was a 1 hiding in front of that arctangent. Likewise, there's a 1 hiding in front of the natural log. So now when we make our choice for u and dv, I'm going to say there's really one good choice to make. Let me remind you of the bad choice, as I did before. If dv is natural log of x, to find v, you would need to anti-differentiate natural log. But if we knew how to anti-differentiate the natural log, we would not be using integration by parts. So instead of choosing the natural log of x to be dv, the only choice we can make is u as natural log and dv is 1. That forces v to be x and du 1 over x. So applying integration by parts, we get uv minus the integral of v du. So in this case, the x's cancel, and the antiderivative of 1 is simply x. Now that we've seen a few examples involving integration by parts, you might be noting that all of our examples have been indefinite integrals. But it turns out we can apply the same exact technique and idea for evaluating definite integrals. Integration by parts for definite integrals has the same formula we've previously been working with. We just have to make sure that we are evaluating appropriately. So turning our previous example into a definite integral, let's make sure we can evaluate. Using integration by parts, much like we did a moment ago, we are going to choose dv to be 1 and u to be the natural log of x. So du is 1 over x, v is x. Applying integration by parts, we have uv, so x ln of x, evaluate it from 1 to 2, minus the integral of v du, once again evaluate it from 1 to 2. So for the first part, we now need to do more than simply cutting and pasting it down. By the fundamental theorem of calculus, we evaluate at 2 minus sign evaluate at 0. So we would have 2 ln of 2 minus 1 ln of 1 minus, when we evaluate the remaining integral, the antiderivative of 1 is x, and we need to evaluate that from 1 to 2. Now note the natural log of 1 is 0, so this term vanishes. We have 2 natural logs of 2 minus, we substitute in x is 2, minus sign, substitute in x is 1. Which gives us the value of our definite integral as 2 natural logs of 2 minus 1. So just to recap, when it comes to evaluating definite integrals in integration by parts, it's simply a matter of making sure to evaluate appropriately. So that completes our current discussion. In our next video, we'll look at a few more, I guess I would say, slightly involved examples, seeing scenarios of applying integration by parts multiple times, and another very common type of example. So stay tuned and take care.